Hello everyone, and today we are going to start our final section of our wave units, and that's going to be light reflection and refraction. And so now we've just spent some time talking about what electromagnetic waves are, which are basically all light waves, whether they are visible or not. Now with reflection and refraction, we are going to focus on the visible portion. Another thing to mention as well is reflection and refraction can occur like in sound waves and things like that, in which you can have, like echoes, like that'd be the reflection of sound. So I'm not going to say that this doesn't occur in those waves either, but we're going to focus on the light piece of it today, on those electromagnetic waves. All right, so let's first look at the light refraction. What is light refraction? So light refraction is the bending of light waves as they pass from one material to another. And now one kind of important piece of this is this bending only really occurs when they enter at an angle. So that might be an important piece for you to kind of make note of, is this bending only occurs when at an angle. And that's an important piece to think about in the sense, and that's what's being shown here on this image below that. Okay, so what we can see is that this wave is traveling and it's entering at an angle, right? It's not this, there's this part on this side and then there's the part on this side. It's entering in at an angle. And because of that, what you can kind of see is that there is this bend, these kink in these wavelengths, right? So you can see that they're roughly this far apart in the beginning, right? And then they get much closer after we've passed through whatever this medium, excuse me, might be. What's happening is right here, so if I can get my focus on for you guys, is right here, and you can see that along the way in some of those other points, you can see there's this bend because part of the wave is being slowed down first. So it's kind of like if you were walking and if just one side of your body slowed down, the other side went a little bit faster, you kind of start to turn. And that's how we actually turn. You just don't think about it. When we're trying to pivot and turn, we stop one motion of our body and we pivot on the other side, and then the other side of our body swings around, right? And that's what's happening with their waves. So that's what causes it effectively to turn, which then we perceive as the bending of light. So with that, light refracts because its speed changes. All right, it either speeds up or it slows down. Frequently for us, it's going to be slowing down, but it could be speeding up if it's leaving a medium that's denser than a vacuum. And that's where you could have it being sped up. Typically, we'll have a scenario where it's coming from a vacuum or an air, where it's going to have really no resistance, and so then it'll be going into something thicker like glass or water or some other type of material. And we have a general equation for that, and that's going to be shown there on your screen. N equals C divided by V. So what do all these things mean? The C stands for the speed of light in a vacuum, so completely empty space. There's nothing there to interfere with it. V is the speed of light in that substance, so whatever it might be. It could be water, it could be glass, whatever that other medium is. And N is the index of refraction. Now the N, that's the kind of a value for the number, and there is not going to be a unit on it. On the right hand side, you'll see a chart with all these different indices of refraction. Sometimes I'll ask you to find what is the index of refraction of this material. Other times I'll give you that and you'll have to find the other pieces, right? How fast will light travel through this? With this particular type of equation, I typically have you determine what is the index of refraction. All right. And you can see, vacuum is 1, right? So we're not going to have an index of refraction below 1 in the sense of we're not going to have something that has lower resistance than a vacuum. Okay. And then air, a lot of times we'll use in that place if it's traveling through air, just use the number 1 for that, because as you can see, there's a little bit there, right? You can see that there's this 3 right here. That is such a small impact that for our purposes, it has literally no impact. All right. And then we'll see a lot of them here, and I'll always provide a table for you guys on the indices that you may need for a given assignment. So the speed of light in a vacuum is 300,000 kilometers per second, right? That's super fast, right? The speed of light in glass is 200,000, kilometers per second. So we see that visible slowing down. So what that means is our index of refraction for this specific type of glass will be 1.5. And if we then look to identify, like we can say, oh, well, now that we know that index of refraction, what is it? Maybe we want to know what type of glass. It's somewhere between a quartz glass and a crown glass, right? There's these different types. And so, and you know, it could maybe even be a type of plexiglass. We see those are there. So you could get a good idea of what it might be. Of course, you might have colors and things like that to help us help really identify what some of these substances might be, which is something you can do, which is pretty cool. So looking at it a little bit further with the refraction, light must strike the surface at an angle to refract. I mentioned that before. If the light strikes straight on, so at a 90-degree angle, it will not refract. So that's sort of represented in our image to the right with that green line. Okay, let's say that was a green laser. Now we call that green line the normal line, and so that's always going to be present on our diagrams. But let's just pretend that that is an actual laser that's traveling, or some beam of light. It's not going to bend. It will slow down. So let's say this, the kind of that red, pink, whatever that is that it's going into, that, let's say it has a higher index of refraction, so it's going to slow down that wave. Then yeah, this part would be traveling slower than this part up here, but there's no angle, so it won't bend because it's being equally slowed down. Whereas when it's at an angle, so this blue line, you can see there's this little bend because part of it's being bent first, or slowed down first, I'm sorry, then the other was just causing it to slow down. So here's a couple other rules that we can have for refraction. If the speed of the light decreases, so we're slowing down, the ray bends toward what we call the perpendicular. That was what that green line was before. We oftentimes would call that the normal. All right, so in this scenario, we can see that we have our light coming in this direction. It hits this part, so we're going from air to glass. It's slowing down because glass will slow down that wave. And you can see now that we have this bend of our light, and now it's getting closer to the perpendicular. All right, because now the distance between here to here, so this distance is now smaller once we're in the medium, in that different medium. All right, so that angle changes. It's now bending down towards that particular normal line. Now the other rule that's there then is if the speed of the light increases, the ray bends away from that perpendicular or normal. So here's a kind of a situation where it might happen, in which we have air shining through maybe like a glass of water or something, in which now you can see it definitely bends down just like what we had before, but now after it's passed through, you can see now this blue line that's there on the bottom, right? So now this blue line, it's now getting larger than when it was in here. So we kind of have this bend up and away, kind of lifts up a little bit if you want to think of it that way. And in reality, this actually is now going to be on the same path as it was originally, because it's going from air to water to air. So all it really did was it almost just shifted over, right? Like if we were to draw this line straight, it would have gone on this kind of trajectory, but now it's going to be a little bit lower and traveling. So all this really did by shining it through this is it just took the light and it's almost like I shined it over a little bit to the side. Okay, but it does straighten out, which is pretty cool, and we'll look at that in class. And then the next thing with refraction, the more the speed of the light changes, the more the light refracts. And so this is an important piece to kind of consider. So, and that's part of with what how a prism works. So the first thing is the light can change more based off of the index of refraction, right? The higher the index of refraction of the material, the greater that change. So we just kind of looked at that. The other piece is going to be the type of color. So it actually affects colors differently. It bends red light less than it's going to bend like blue and violet light. And the reason is because all colors of the light move at the same speed, right? The speed of light is the same. What causes the change in that prism will alter the wavelength, but not its frequency. Well, what turns out is the like violet and all those, have a much shorter wavelength, and they end up actually interacting, and they have higher frequency too, interacting with whatever the medium they're traveling through more, which causes them to bend even more than the lights of the longer wavelengths. They're because each of those wavelengths is hitting more and more and more, so there's this bigger bend, and that's what we can see in this prism here, in which we have our red light bending a little bit, but not as much, but then our violet light here and our blue light bending quite a bit more, because they actually interact with the molecules within the medium more. In this video, I'll also link another video that goes through and kind of explains that and adds a nice little graphic for you guys as well. So with refraction, we have our light refraction diagrams, and there's a lot to kind of identify of what's on here. I do see that that's cut off there in the bottom with that little box that I have here. This right down here, that's a little cut off. That just is normal. That's the normal line. So the normal line is the perpendicular, so the 90 degrees, that's the dashed line on our diagram, from the boundary of the surface. So that's that black line that I have there. So it forms that right angle, and that allows us to measure the change in the angle after it enters into the medium, in this case from air to water. We have our incident ray, which is the incoming beam of light, so that's the blue on our diagram. We have the incident angle, which is formed between the normal line and the incident ray. So that incident angle is represented by the letter I there on our diagram. All right, so that's like the original angle. And then there's the refracted ray, which in this case is the red line on that diagram on the right. And then we have the refracted angle, which is the letter R in our diagram there, which is formed between the normal line and that refracted ray. And that's where we can see what change in angle did we have, and that can help us find what that index of refraction is. So with that, we have something called Snell's Law. Go figure, it's named after someone who had the last name Snell, who looked into this, as a lot of things in science are. And it's the relationship between the angle of incidence and the angle of refraction and the refraction index. So what this does, and now there's the formula below, it looks really complicated, absolutely. I'm going to provide to you an automatic calculator for this that'll also be linked within here. You just need to be able to identify those variables and then be able to determine what does that number mean that you get as a result. All right, so we have our Ni. So this Ni, that's going to be the index of refraction for our first medium, or like in our first medium. This sine theta I, that's going to be that original angle. And then we're going to have NR, which is going to be our new index of refraction, so whatever is for the second medium. And then that sine theta R is going to be the new angle that we get. All right, so one way to kind of think about that, if you want to kind of write that out, this is the index for medium number 1. This is angle 1. And then this is index 2. And then this is angle 2. All right. So we're going to go ahead and find the answer to this question. So just an example problem for you. So we have our equation listed above, and what we've been told is that we have our original starting point. Our original index is air, which is 1. That's what we're taking a laser and we're shining it through the air. And then we have our original angle at 75 degrees. So we took our laser, we shined it at 75 degrees, and then we have our new angle. So we measured the angle of the light as it's bending, and we found that to be 60 degrees. So we had that 15-degree difference. We want to know what would be the index of refraction for material that would produce this result. So to do so, you're going to use that automatic calculator, that Snell's Law automatic calculator. So that's going to pop up in this video. And you are going to set this up to put in the information. Now, what you're going to need to change is, so this is kind of how it opens up for you. What you're going to want to do is you're going to want to make sure you change the calculate to be N2, because that's what we're trying to find, right? If we go and think about so what we are trying to find what our NR is, which is our second index. And that's where we're going here. So make sure you change this to N2, and then your job is to put in those values, click calculate, and then you'll find the answer will show right here. So go ahead and do that now. And we should find it to be 1.1154. And now there's not a unit for this because it's a ratio. It's telling us that, all right, our light traveling through this will be slowed down by a factor of 1.11. So it'll go a little bit slower than it would in the air. And so with this specific scenario, so now I have an image of what this scenario might look like. So you have that laser shining at that 75-degree angle, as you can see with that digital protractor. It's hitting that surface of the medium of what we don't know what it is. And it's hitting, you can see that bend. Look at the kind of the darker red line. That other one is a partial reflection, which can sometimes occur or frequently occurs with some of those. We don't need to worry about that right now. But you can see now, and then it goes to about that 60-degree mark, which matches what we have. And you can even see that on that diagram that I have there, we have our index of refraction at 1.11. So it's nice that that tracks for us, and our answer matches what we should expect. All right, and then the very last piece is looking at light reflection. So the reflection, this one's a lot more straightforward than refraction. So light is just the bouncing back of a light ray after hitting any surface. So the angle of incidence equals the angle of reflection. So basically, whatever angle we hit it at, it will bounce back at that same angle. And actually, if we go back and we look at our previous question here, you can see now if we look at that faded one, you'll see that that angle matches what it was on the other side. We get that nice little, look, almost like it's skipping off that surface, and that's basically what a reflection is. It mirrors it, and that's how you get that mirror images. It actually causes it to invert, but it flips on the exact same size. Or side, I'm sorry. So kind of connecting reflection to colors. So when we see a color of an object, that means that this color is being reflected. So when we see something as green, that means we're seeing only the green wavelength. All the rest are being absorbed by that particular object. So like trees are going to reflect green light. And then whereas other wavelengths will be, so it'll change. Whatever the color it is, that's the thing that's being reflected by it. And so if like your favorite color is red, like let's say you really like red shirts or I don't know, then that what you really are liking is you're liking objects that reflect red light. Objects that are black absorb all of those wavelengths, which is why you think on a hot summer's day, a black shirt gets really warm, or you think of like pavement, like roads, why they get so hot in the summer is because they absorb all of those wavelengths, which means they're absorbing all of that energy, which is a whole lot. All right, and then in contrast, white does the exact opposite. It's actually all of the wavelengths together that we see. So white is reflecting all of them, and we see that as white, and that's why white tends to be one of the colder actual colors as far as absorbing energy, because it's reflecting all of it. It's not actually absorbing much at all. And that does end our video on light reflection and refraction. If you have questions, absolutely let me know, and I'll help you out. Otherwise, have a great day. Thanks for watching.